Steel glows a brilliant orange as it emerges from the furnace at 1700 degrees Celsius. The controlled heating and cooling of steel, a practice that dates back to ancient blacksmiths, transforms ordinary metal into something extraordinary. The first phase begins with austenization, where steel is heated to temperatures between 1500 degrees and 1900 degrees. At this critical temperature range, the metal's crystalline structure undergoes a remarkable transformation. The iron atoms rearrange themselves from a body-centered cubic structure into a face-centered cubic arrangement, creating more space for carbon atoms to dissolve into the matrix. As the steel reaches its target temperature, it enters the soaking phase. Here, the metal must remain at temperature for a specific duration, typically 1 hour for each inch of thickness. During this time, carbides and other elements distribute themselves uniformly throughout the material. This uniformity is crucial for the final properties of the steel. A piece of steel rushed through this phase would be like an undercooked cake, inconsistent and potentially flawed. The next phase is where the magic truly happens: quenching. The heated steel is rapidly cooled, usually in oil or water, though sometimes in other media like polymer solutions or even forced air. The temperature plummets from over 1500 degrees to about 150 degrees in mere seconds. This dramatic cooling forces the carbon atoms to become trapped in a new distorted crystal structure called martensite. The transformation is so rapid that the metal literally transforms faster than the speed of sound through the material. But this newly hardened steel is too brittle for most applications. Like a spring wound too tight, it needs relief. This brings us to the tempering phase, where the steel is reheated to a lower temperature, typically between 300 degrees and 1300 degrees, depending on the desired final properties. During tempering, some of the trapped carbon atoms are allowed to migrate, relieving internal stresses while maintaining much of the hardness gained during quenching. The final phase is the cool down to room temperature. This must be controlled carefully to prevent thermal shock or uneven cooling that could lead to warping or cracking. The steel's surface temperature gradually drops from tempering temperature to about 70 degrees over several hours, allowing the metal to stabilize its microstructure. Through these carefully controlled phases, ordinary steel is transformed. A piece that started with a hardness of 15 on the Rockwell C scale might now measure 60, harder than a file. Its tensile strength could increase from 70,000 psi to over 200,000 psi. The steel's microstructure, viewed under a microscope, reveals a complex landscape of martensite needles, retained austenite, and carefully distributed carbides. This transformed steel will go on to serve in countless applications. It might become a precision cutting tool, capable of slicing through metal like butter. It could form the core of a massive industrial die, stamping out thousands of automotive parts without wearing down. Or perhaps it will become part of a critical aerospace component, where its enhanced properties will help ensure the safety of countless passengers. The phases of heat-treating steel represent one of humanity's greatest achievements in materials science. From the precise control of temperature to the split-second timing of quenching, each step builds upon thousands of years of metallurgical knowledge. What begins as a simple piece of iron alloy emerges as an engineered material, its properties precisely tuned to meet the demanding requirements of modern industry.